So good day guys, welcome to today's lesson. In today's lesson we are going to be defining the materials. So you can see on this menu bar we have the edit, view, define. So let's go to define now. We've defined material which we did in the last video. Next thing we want to do is our section properties. So for frames we have columns and beam. Tendons we have the tendon for post stress. Then for slab, then for deck, wall, reinforcing bar, so you can define anything you want. So in this case, we are going to be defining the major things we need, so which is the frame. So you can see we have the concrete beam, concrete column, steel beam, steel column. So I'm not using this. I will delete these two, delete them, and leave my concrete there. So I can add a new property. Just create add and select the one I want and choose whichever one. So for example, I have beam 230 by 600, and I'll choose the material I want. Okay, you can see the material I want. So I want this for flexure, and change my depth to 600 and my width to 230. Okay, so we have this 230 at width. Okay, now we have what we call property modifiers. Now if you go to Euro code 8, that is for seismic. So Euro code 8, that's 4.3 plus 4.37. Now it has told us that unless a more accurate analysis of the cracked element is performed, the elastic flexural and shear stiffness property and masonry elements may be taken to be 1/2. So we all know that for our concrete member to fail, reinforced concrete member to fail, the steel must yield. So we need to account for cracking members. So this is one advantage of using ETABS, that you can easily account for cracking members. But instead, if you are using STAR, before you can account for cracking members, it is a bulky process because you have to go to specifications, stiffness reduction, and you are assigning it one by one. So it's a little bit cumbersome. But in ETABS, you can just apply it from the definition. So now it has told us to take it as 1/2. So you'll be seeing some videos, people using the American code. The American code has done an experiment that for beam you can use 0.35, for slab 0.25, for column 0.7, and shear wall 0.7, 0.35 for cracked, then uncracked is 0.7. But the code has given us a clock that unless an accurate analysis, so over time you can decide to use it yourself. You can decide to use your own code, like Australian code is using 0.4 for beams and 0.25 for slabs, then 0.6 for columns. So you can decide to choose whichever one you want. You are the engineer, you make the decision. It's just for you to reduce the stiffness. So the stiffness must always be less than 1. That is your duty. So in this case, this itself should use 1/2. So 1/2 in British English means 0.5. So we'll come to this and we'll go to property modifier. So for beams, all we are interested in doing is changing our M2 and M3. So I'll just change it to 0.5 and 0.5. Now we have what we call torsional constants. I'll be explaining about torsional constants. So I'm going to reduce my torsional constant. Okay, so I'll reduce that and click OK. I'll explain it in the next video. Now the next thing I want to do is come to reinforcement, and I'm going to change. Okay, so since we've created the rebar 500, I don't need to change it. I don't need to change this. So I'll come here and change it to beam. So initially it was designed as column, so I'll change it to beam. Okay, so now the cover of longitudinal. So what it means is, let's go to, let me open paint. Okay, so that I can explain some things to you. So we have our beam like this. So right, this is the beam section. Now this is the stirrup. Let me change the color to the stirrup. So this is the stirrup. Right, now let me put this as the reinforcement bars. Okay, 1, 2, 3, and also I have here 2, 1, 2, and 3. Now, so what it's telling you, look at what it said. It said cover to longitudinal group centroid. So I can get my cover. So this is the cover from this bottom here, this bottom to the centroid of this rebar. You get to the centroid of this rebar. That's it. But in this case, let's assume we have a spacer bar and we have something here. So you can put the centroid at this place. This is the centroid. But most cases, we always try to have one layer of this. But in case we don't, you can always do this. It's just an explanatory. So for example, from here to here is 25 mm. Now we have 25, and my stirrup is 10 mm. That is 35 already. So 25 plus 10. Okay. Now let's say for example, this is 16 mm. This is 16. So plus 8. 16 divided by 2. So all I have now is going to be 43. So I can just round it up to 45. Okay. So I'll change this to 45 and change this to 45. Now this is for ductile beams for earthquake. Maybe your code has said the minimum reinforcement you should have at the corner is this. You can just put the reinforcement area here and you move on. Okay, so you click OK and you set the properties. Okay, same with the reinforcement, we've done that. Okay, then we'll click OK. So we have this beam. Now I can decide to add a copy of it. So for example, I want to add a copy of this beam. So when I add a copy of these beams, the properties are copied from there. The reinforcements are copied from there. So all I just need to do is, maybe for the roof beam now, roof beam, I will just change this to 450 and click OK. So now I can delete this beam. I'm not using it. Delete it. Yes. Now for the column too, let's say for example now I want to modify this column. So I'll just come here, modify it, and choose my column. So I can just say column 300 by 750. So just a trial column. If it fails, and I'll put its compression. Okay, then my depth. Now always make sure your depth is the bigger part of the column, 750, so that you can easily interpret the bending moments. If you do it, it will be confusing. If you use the depth as the width, it will be confusing. I'm sure you'll be asking, what if the major axis is facing the y direction or the x direction? Then we have a rotate command that will help you. Okay, so now we have the width as 300. Okay, so next thing I want to do is go to property modifier, and since the code has said I should use my reduction factor, so I'll change this to 0.5 and change this to 0.5. Okay, but I won't touch the torsional constant of column. Is 1 like that, so I'll keep it. Okay, then reinforcement, I'll change this, so this is column here, rebar 500, rebar 500. Now we have two options. You can either check your column or you can design it. So if you check it, it means, for example, if I put it on check now, I have to provide the area of steel. For example, now it's telling me to provide 3 in this phase and 5 in this phase. So if ETABS performs the analysis and the design, if this area of steel I've provided is not sufficient, it will fail, or preferably it is better for me to design it. So once I design, I don't need to tamper with all this. So let's say I can just put 16 mm. 16 mm. Okay, you can see the area of steel there, but we are just designing it. So for my cover, I'm going to use 40 mm. Okay, my cover. So I'll click OK and OK. So I'm assuming I'm using one column from ground to the roof just to save form work, and I won't be and it creates easy alignment. Because it's an high-rise 15-story building, or 16 rather. So this is what we have. So we defined our frames. Now the next thing we want to define is our slab. Okay, so let's go to slab section. So delete this. Now modify. So we have slab. So let's start with slab 150. Choose what I want. I want flexural. Okay, so I'll change this to 150. Now we have different types of slab. We have slab shell thin, shell thick, membrane, and layer. So the common type we use here is shell thin and membrane. Now what membrane means is transferring all the load to the beam. That means the slab is not taking part in flexure. For shelving, the slab is taking part in flexion. So let me give you an example of what you know. You remember in start you have floor load and you have plate load. So floor load is the membrane, plate load is the shelving. So shelving transfers load based on stiffness, while membrane transfers load based on yield line. But practically, your slab is going to behave like a shelving because it takes part in flexion. So change flex, then property modifier. So since our slab is going to behave like a diaphragm is what transfers lateral load to the bracing element. What we do is reduce this. So divided by 2. American code will say you use 0.25. It doesn't matter. The main thing is for you to reduce your stiffness from 1 to anything lesser than 1. It doesn't matter. So that if you take it as 1, let me just explain the reason why we place this. Now, if you take it as 1, you are saying your member is fully stiff and it's never going to crack, which is not, you know what is going to happen on site. In site, there will still be microstructural cracks and everything. So you need to account for all those cracks. And secondly, if you use a fully rigid, a fully stiff member, that means you are underplaying the effect of deflection. You are saying that, oh, this is not going to really deflect because you will never get the real deflection there. So you can, by the time you can do an example of a slab or a beam with reduced stiffness and see with reduced stiffness and without reduced stiffness and see the effect of a deflection. So yes, in sense is that if you reduce the stiffness, lesser load will go to that member and lesser reinforcement, but you get more deflection. But if you don't reduce it, you get more load to the member, more reinforcement, but smaller deflection. So that is it. Then it is advisable to always reduce your stiffness. So I'm using 0.5, 0.5, 0.5 and 0.5. Okay. So but if you are using membrane, you don't need to reduce the stiffness. If you are using membrane, you don't need to reduce the stiffness of the bending because there's no flexion, there's no bending. All the whole load are going to the beams or the columns, whichever one you are doing. Okay. So we have okay with this. Now we are done defining this. Now you can choose the type of slab you want. If it's a drop, stiff, this and everything. But in this case, it's going to be a normal solid slab. So I'll select this and click OK. So I'm going to copy it again and choose slab 175. So just change this to 175. Okay. Also add a copy again at slab 200. Okay. Slab 200 and change this to 200. So all the property we've done at this point, click OK. So modify and change this. So we've defined the slab and let's define the wall. Okay, so section property, wall section. So we have the wall defined, so we can just modify it. So let's say our wall thickness is 230. Let's say 230, and it's a compressive member, right? So we select this shelving. Let's change this to 230. Okay, so modified property. So now we have the membrane and we have the bending. So generally we know that shear wall does not have out of plane bending. That means it does not bend like a retaining wall. It doesn't bend like a retaining wall. So we can reduce this. So we can reduce the reinforcement. Okay, so 1/10.1 or even anything lesser than it, so that it doesn't attract any bending for it. Okay, so this is what we have now. But because we know this is like a column, so it takes the wind, the lateral load. So I want to have a cracked column. I'll just make it 0.5, 0.5 and 0.5. So if you decide to make it a crack, it's just that you attract more load, but you will never account for the displacement or the deflection, which is going to make your design uneconomical and unpracticable. So click OK, and this is what we have. So we have this shear wall. Okay, so thank you for watching today's video. In the next video, we'll be talking about torsional constants. Okay, thank you very much.